Hello, everyone. Thanks for joining me again. This time I'm going to tell you a little bit about electromagnetic waves. Okay, so based on what we've already talked about, you hopefully have come to the appreciation that light is a wave. Even though in a week's time or thereabouts, we're going to start talking about light as a particle. For now, we're going to keep on thinking that light is a wave. So in other words, historically, this would be like late 19th century. Okay. Now, since light is a wave, it has to obey the universal wave equation, which is V equals F lambda. The speed of the wave, which is, of course, the speed of light, is going to be equal to the product of the frequency and the wavelength. Light, as you probably know, is part of a spectrum, right? The light spectrum going from red, orange, yellow, green, blue, indigo, violet. Now, that's the visible spectrum, but in fact, there's stuff outside of that you probably know of, like past red, there's infrared, past violet, there's ultraviolet. And in fact, it goes in both directions to things that we obviously can't see with our human eyes, but we can create technologies so that we can observe those frequencies. The color of the light is determined by its wavelength or equivalently by its frequency. So for example, red light has a different wavelength than blue light, and so on and so forth. Is that we saw from when we talked about Faraday, that there is this relationship between electric fields and magnetic fields. Specifically, when we have a changing electric field, we will produce a magnetic field and vice versa. So this is actually really, really key. And this kind of gets us into the idea that light is an electromagnetic wave. So here's a picture that kind of describes what light might look like if we could basically, again, we're thinking about it as a wave and we're freezing it in time. Okay, so you can see that there are two sinusoidal functions going on here. The red one is to represent the electric field, and the blue one is the magnetic field. So in other words, calling light an electromagnetic wave means there are literally two waves happening simultaneously. One of them is an electric wave, the other one is a magnetic wave. And the direction is, I guess that's purple, pointing off to the right there. And that's essentially, that's the direction that the wave is going. So it turns out that the electric field and magnetic field are perpendicular to each other. Furthermore, the two waves have the same wavelength. So again, I've tried to represent that there. And the direction that the light is traveling, or the direction that the waves are traveling, is perpendicular to the direction of both. So in other words, both the electric field and the magnetic field are transverse waves, and they're traveling in a direction given by what's called the wave vector. If you look carefully, there's actually a right-hand relationship here. You can do this with your fingers, for example, your index finger going in the direction of the wave vector, your middle finger going in the direction of the electric field, and your thumb going in the direction of the magnetic field. Okay, so if you rotate your fingers around, you'll actually see that it follows the same way as the diagram there, and that's not on accident. Again, because this is a stationary image, you might not get a sense of this, but the idea is that as the electric field changes, so too does the magnetic field. So it's not really reasonable to try and disentangle them. Okay, so since we have, if I just consider the electric field for the moment, then we come to something called polarization of light. Light is said to have a polarization, which refers to the orientation of the electric field. Now, this can be a little bit tricky because a lot of light sources are actually unpolarized. So for example, the sun, most LEDs, most flashlights, unless they have some other element, some element built into them that polarizes the light, certainly the sun doesn't, of course. But what you get out of that is unpolarized light, which means that the electric fields from those sources are pointed randomly. So I'm just going to use this. Imagine if this were light, if this represents the electric field being vertical here, this would be polarized light traveling towards you, okay? Polarized light this way. Or I could have polarized light going this way. Unpolarized light means that I have a whole bunch of waves stacked on top of each other, one where the electric field is going this way, one where it's this way, one where it's this way, one where it's this way. So it's just completely random. The electric fields are all randomly oriented. Lasers, on the other hand, are special because of the physics behind them. The electric field out of them, the light out of them has its electric field linearly polarized, strongly linearly polarized. You can actually tell a good laser from. Okay, so what does this mean? So in this case, this is an image of a lake outside, and although it looks like it's covered with snow, that's maybe not the best. But in any case, on the left-hand side, this is an image of or a schematic of the light coming from the sun. So this is sunlight, and you can see that it kind of looks like a whole bunch of squiggles, but those squiggles are representing the electric fields, all jumbled up, right? They're all randomly oriented, all in all kinds of different directions. However, here's the cool thing. If that light were to reflect off the surface, and you measured the polarization of the light that way, you would actually see that the light is linearly polarized. So ice can act as a polarizer. It can actually take randomly oriented light and turn it into linearly polarized light. Okay, so that previous schematic kind of hits home this idea that polarization, I can talk about it this way, I can talk about it this way, I can talk about it any old way, but really talking about the direction of polarization only makes sense if you have some kind of a surface or a coordinate system. So normally this is the kind of picture that we look at, where we have the light coming in from the left-hand side, bouncing off the incident surface, which was the sheet of ice in the previous picture, and then we have the light reflecting off to the left there, to the right there. Sorry, on the right-hand side. Apologize. But you can also notice that if it's a transparent surface, right, like say water or maybe glass, then some of the light will reflect, but some of the light will also transmit. And so I don't know if you can see this clearly, but essentially, what we're saying here is that the light which is reflected off, we're calling that S polarized light. And the light which transmits through we call P polarized light. Okay. And the incident light may have, again, maybe sunlight, which will have some combination of S and P, right? S and P. Could be, again, it could be like randomly oriented. Doesn't really matter. So one thing to help you kind of remember these letters is S. The mnemonic, this comes from one of my professors in university. The mnemonic to remember is that S is skip. So if I have a surface like this and I have my light coming in, S polarized light will skip off. So this will be the light that reflects off the surface. Okay. Whereas if I have P polarized light, which is like this will plunge in and through the surface. So this is P polarized light, okay? You could also call it vertically polarized, which is fine. But again, it all actually depends on the orientation of your surface. So yeah, okay, so this is P polarized light. It's plunging into the surface. This is S polarized light. It's skipping off the surface, okay? So I just said that. So again, if you're looking at reflection off a lake or something, what you're actually seeing is S polarized light. Only S polarized light is the one that actually reflects off the surface. P polarized light does not. P polarized light basically goes into the water, into the surface, or it gets absorbed. All right. Now, full disclosure, even though my professor used these words S and P, That's not actually what they like. S doesn't stand for skip, P doesn't stand for plunge. Those are just mnemonics to help you remember them. In actuality, P stands for parallel, and S comes from the German senkrecht. I think I pronounced that right, or close, which means perpendicular. Any Germans out there will let me know on my pronunciation. So that's basically what those actually mean. So, but from my feeling, like in terms of thinking about what the light is actually doing, I actually prefer skip and plunge, even though they're not the correct words, because they at least tell me a little bit about what the light is doing. Okay, so I've talked a bit about how you might make unpolarized light polarized, and if any of you have any experience with filmography, you may have done something like this already. A lot of cameras, older ones especially, used to have polarizing filters on them. So basically a thing that you would put in front of the lens or something behind the lens. And that would allow you to basically change not only the amount of light, but also the polarization of the light that's coming into that was coming into the camera. Most of the time, this was just used to adjust how much light was coming in. So in other words, changing the intensity of the light. But you can actually do some pretty interesting tricks with polarizers, which I'll talk a little bit about right here. So a polarizing film is really just, it looks like a plastic sheet that's kind of dark. I'm afraid I don't have any right on me right now, but if you imagine light as being P polarized or S polarized, then one of these two things will be extinguished in a polarizing film. There's a really great video that I saw on this recently, and I'm going to link it in here because this is really cool. Because you might not. First of all, you have to buy that light is acting as a wave, but how this light can be extinguished by a polarizer is like pretty amazing. So there's a fellow who did a video with a slinky. You got to watch it. I'm going to link it in right here. Hope that was the right corner. So as you saw on that video, the filter that he was using, the polarizing filter, was actually made of a bunch of wooden slats. And polarizing film is similar in that it's made of very small wires or nanoparticles, and those basically have an orientation to them. So they'll, again, in a very simple case, a linear polarizer, those wires will be all lined up in one direction, like vertically or whatever. So if you think about it, if I have a polarizer which is oriented this way and my light is oriented this way, well, that's not going to get through. Just like in the video, that's not going to get through. But this one will. A wave like this will be able to go through those wires, right? That's basically the idea. In terms of how much light actually gets through, this is a very simple and minded equation, but nonetheless, it's actually pretty powerful. So for unpolarized light, again, sunlight, that will have some intensity, I0. And so the sun's polarization is all random. We have one like this, one like this, one like this, whatever. And as that reaches our polarizer, only the waves that are polarized like this, or at least partially polarized like this, will make it through. So in aggregate, half of our original intensity will make it through. And this is why those polarizing filters, that's one reason why you can use a polarizing filter on a camera. You can use it to extinguish half of the light if there's too much light. Now, there's actually a little bit more to it, and that is if you have linearly polarized light and then you pass it through another linear polarizer, then what's an interesting thing is that the angle between, let's say I have linear polarized light like this, but my linear polarizer is oriented like this. So now, as this linearly polarized light gets to the linear polarizer, then only part of it is going to pass through. And the amount that passed through depends on the angle between the electric field and the direction of my polarizing film, right? So the angle here, basically, that I've got right there, that would basically tell me how much light is going to pass through. This would mean no light is passed through. This would mean all the light is passed through. So by adjusting the angle, actually you adjust the, you don't adjust the light, you adjust the polarizer, but whatever. So, but the angle, the key though is the angle is what's going to tell you how much light passes through if it's linearly polarized. So that gives us this equation. So it basically goes as the square of the cosine of the angle. Okay, so some applications that you might find interesting, and some that you may have actually had some experience with, are polarizing sunglasses. So if you buy even like reasonably priced sunglasses nowadays, most of them come with some kind of polarizing film to reduce glare. I mean, so in one sense, polarizing sunglasses just in general have kind of like a tinted plastic or tinted glass on them, and that's just to reduce the amount of light that gets through. But by adding a polarizing film to them, you can reduce glare. And if you think about it, if you're out, I don't know, outside under certain circumstances, where are you likely to get glare from? I mean, think about it if you've ever been driving on a sunny day. Where do you see glare coming from? And how, if you were designing sunglasses, how would you want your polarizers on the glasses? How would you want them to be oriented? Would you want light that was S polarized to get through to your eyes, or would you want light that was, what did I say? Would you want light that was S polarized to reach your eyes, right? So light that had bounced off of something on the ground and bing like that. Would you want that to reach your eyes, or would you want light that was P polarized to reach your eyes? You'd want the light that was S polarized, because this is the light that's going to be bouncing off, say, puddles on the ground, or if there's, especially on a lake. A lake is a really good example of this. If you're on the water, light that bounces off the water and into your eyes, that's the glare. You want to reduce that if possible. So in most cases, good sunglasses are polarized this way, so that this light does not get through. If you've been to a 3D movie, if you paid the extra money and you went to a 3D movie where they give you the glasses, then how those are normally made is that there's a polarizer for each eye, and one is oriented this way and the other is oriented this way, or this way if you prefer, okay? So that if you were to look at the image on the screen, this is actually quite fun if you ever do it. You can, take the glasses off in the middle of the movie just to see what it looks like. And it's very blurry. It almost looks like it's a double image, because in actuality it is. One of these two images are overlaid on top of each other. It's slightly off center, but the difference is that one of them is the light from that image is polarized in one direction, and the light from the other image is polarized in the other direction. So again, like this. So this makes sure that the glasses basically filter out the wrong light, so that the image that reaches each eye will then in your brain create the 3D image. So that's one thing that you can use polarizing 3D glasses for. LCD screens also use polarizers, and these things called wave plates, which is basically a way of twisting the orientation of light, twisting the polarization of light. So here's basically a stack. If you were to basically look at all the different layers that go into an LCD screen, it's the liquid crystal part. So a liquid crystal is literally what it sounds like. It's a crystal structure that has some liquid property. And what can normally be done with a liquid crystal is that if you apply a voltage to it, it actually rotates it in a certain orientation, which is pretty cool. So that basically acts by changing the orientation of the crystals. That actually changes the orientation of the light, the polarization of the light as it passes through the crystal. And so if you then have another polarizer after that, then that will make it so that the light gets extinguished or passes through. You can actually try this with your monitor. I don't know if this is going to work here, so I'm just going to go ahead and try anyway. I may cut this in post if it doesn't work, but in case it does, here I have my sunglasses, and these are reasonably good quality polarizing sunglasses. So right now, if I look at the screen rather through these glasses, then I actually see the screen just fine. Okay. However, if I turn them like this, I don't see anything. The screen to me is black. Okay. I have to look off to the side just to make sure I haven't gone blind. Okay, so I don't know what you're seeing, but that's what I see. If I look through them this way, the screen is like darker because they are sunglasses after all. But I can see everything clearly. But as soon as I turn them this way, everything goes black. Okay, and that's because these are polarizing sunglasses. And again, depending on the orientation, they either allow the light to pass through or they block it. Okay, here's some things that you can read to maybe get a better appreciation of what I've talked about, as well as a couple of questions to try. Thanks very much, folks. See you next week.